In this lesson, we'll examine how to solve a system of equations by graphing. At the end of the lesson, you should be able to answer, how can I use graphing to solve a system of equations? So let's establish what a system is. A system of linear equations consists of two or more linear equations in the same variable. So essentially, you have two lines. So given the system that you see on your screen, you're asked to determine if the following ordered pairs are solutions to the system. Well, whenever we want to check to see if something is a solution, you can use substitution to determine if it satisfies the equation. But what's going to be important here is that it's going to have to satisfy both equations. So in the first ordered pair, 1, 3, I'm going to substitute that into the top equation, which gives me 1 plus 2 times 3. And I'm checking, does that equal 7? Well, 2 times 3 is 6, plus 1 is 7. 7 equals 7, so it satisfies the first one. But it must also satisfy the second one. So I'm going to do 3 times 1 minus 2 times 3, and I'm checking to see if that equals 5. Well, 3 minus 6 is negative 3. This does not equal 5. Therefore, this is not a solution to the system because it does not satisfy both equations. It would be an ordered pair that falls on the top line, but not the bottom. Right, so let's check if 3, 2 is the solution. Again, substituting this into both equations. Right, so 3 plus 4 equals 7, so it satisfies the first one. And I'm going to plug into the second. See if it equals 5. So I substitute in 3 and 2, which gives me 9 minus 4, and that does equal 5. Therefore, this does satisfy both equations in the system, so it is a solution to the system. Now, let's think about what graphically could happen when we graph two lines. One thing that could occur is that the two lines intersect. If this occurs, there would be exactly one solution. It's going to be the point at which those two lines intersect because it's what they have in common. It's also possible that you have infinitely many solutions where one line falls directly on top of the other, known as coinciding lines. Or you could have two parallel lines. If this is the case, there's no solution because these lines will never intersect to have a point in common. A little bit more vocabulary is the word consistent, and then independent versus dependent. The two cases to the left are both consistent systems because they have a solution. In the one all the way to the left, it's a consistent independent system because it's consistent, it has at least one solution, and then we say it's independent because it has exactly one. Now, the one in the middle, this is a consistent dependent solution. It has at least one solution, and we say it's dependent when it has infinitely many solutions where they're coinciding lines, one falling directly on top of the other. Now, it's important to note that yes, there are infinitely many solutions, but it's not every ordered pair. It's only the ordered pairs that fall on that given line. Now, if there's no solution, this is an inconsistent system because there's no solution. Those points will never intersect. So that's some more sophisticated vocabulary associated with systems. In order to determine the solution to a system by graphing, you're going to have to graph your given lines. So what I suggest you do is you convert each line to slope-intercept form. So I'm going to subtract 2x from both sides, which results in y equals negative 2x plus 2 for my first line. My second line, I'm just going to recopy the original equation here. I'm going to subtract x from each side, which gives me negative y equals negative x plus 4. And then I divide each side by negative 1. When I do that, that changes the signs of everything on the right to positive x minus 4. I'm going to graph this first line using red, and I know that my slope is negative 2 and my y-intercept is positive 2. So it crosses at 2 and has a rise of down 2, right 1, and I repeatedly go down 2, right 1. I could also go up 2, left 1 to get a nice straight line. Now, I'm going to connect that because I'm looking for the points which they have in common. Right, so the second line, I'm going to use purple to graph this one. In the first one, my slope is 4, and my y-intercept is my slope is 1, and my y-intercept is -4. So it crosses at -4, and it has a slope of +1. So I'm going up 1, right 1, up 1, right 1, and hopefully you already see where these two lines are going to cross one another. The point that they have in common is right here. So all you have to do is name that point as an ordered pair, okay? Which would be the ordered pair 2, -2. You could always check to make sure that this is a solution by plugging it in as we did in the first examples. Remember, there are those 3 possibilities for how this could play out. Let's do a few practice problems. So in this system, I've got to first convert both equations to slope-intercept form, which gives me -3y equals -6x plus 3. I'm going to divide both sides by -3, which results in y equals +2x minus 1. Now, you may notice something already. These two equations are identical to one another. Now I am going to graph to get an idea of what the line looks like. Crosses at -1 and has a slope of 2. Put arrows on either end of my line. I'm going to label my line as y equals 2x minus 1. Now, if I drew the other line, it would fall directly on top of this one. So this is a case where there are infinitely many solutions, because every ordered pair that falls on that line is a solution. So if there are infinitely many solutions, it would be fair game to say, so name one of them. So you would just name an ordered pair that falls on that line, like 3, 2. Okay, so there's lots of decimal and fractional ordered pairs that satisfy it as well. The second one, both equations are in standard form, so we need to convert both of these to slope-intercept. So the first one, I'm going to subtract 3x from each side, which gives me 2y equals -3x plus 2. And then I divide each side by 2, which is y equals -3 over 2x for my slope, plus +1. So I'm going to graph that. Crosses at +1, has a slope of -3, would be down 3, right 2. Or up 3, left 2. I kind of count towards the end of my coordinate plane so I can get a nice crisp graph. Arrows on either end. Okay, my second one, I'm going to switch colors to make it easier on your eyes. I'll use red for my second one. Again, I'm going to subtract 3x from each side, which gives me -3x plus 7. So this one crosses at +7, right here. And again, the slope here is -3, so I go down 3, right 1, down 3, right 1, down 3, right 1, down 3, right 1. And I can see where these lines are hitting already, but I do need to graph the line. Now, perhaps you're seeing a drawback of the graphing method already, which we'll talk about in a second. Let's name that ordered pair because it does hit at a nice integer value. So 1, 2, 3, 4. Down 1, 2, 3, 4, 5. 4, -5 is the ordered pair that satisfies this solution. Okay, one more. Straight up practice. You're going to convert the second one to slope-intercept form, which would give me 6y equals -3x minus 12. Then I divide both sides by 6, which gives me y equals -1/2 x minus 2. All right, so I'm going to graph the first one. I'll use purple. Crosses at, this one here, crosses at +4 and has a slope of -1/2, so down 1, right 2. Now, hopefully you notice already that these lines have the same slope. And if you remember from earlier in the course, if If you remember the relationship between two lines that have the same slope, if you don't, you'll see it in a second. So the second one crosses at -2 and has a slope of -1/2. Okay, so hopefully you see that these lines are parallel to one another, and maybe you identified that early on because they had the same slope. If they're parallel, they have nothing in common. No ordered pair will satisfy both lines, so there is no solution to this one. Now, let's look at an example of a story problem that we can use a system to solve it. It says the Parks and Recreation Department in your town offers a season pass for $90. As a season pass holder, you pay $4 per session to use the town's tennis courts. Without a season pass, you pay $13 to use the tennis courts. So we need to write a system of equations where y is the total cost in dollars for x sessions. So let's talk about if you have a season pass. Well, I'm going to say y, because that's the cost, equals, you pay $4 per session, so 4x plus the initial fee of $90. The second one is if you don't have a season pass, your total cost is y equals, you pay just $13 per session. This word should be session, not season. Doesn't make sense. All right, now we need to solve this system, so we're going to do it by graphing. So we got to consider how we set up our coordinate plane. Okay, so I just numbered my coordinate plane on just the first quadrant. So I chose to count by 10s on the y-axis and by 1s along the x-axis. So I'm going to have to be careful as I graph these lines. So as I graph the top one, it crosses at 90, which would be right here, and it has a slope of 4. So if I go up 4, I've really gone up 40, so I'm going to have to go right to 10 to make that be equivalent to 4. Think about that, 40 over 10 is equal to 4. All right, so I'm going to connect that. And the other one would have y equals 13x would cross at 0, 0 and have a slope of 13. So I'm going to go up to 130, and again I have to go right to 10 to make that be equivalent. Because again, think about that, 130 over 10 would reduce to 13 for my slope. All right, so I'm going to graph that, and I'm going to connect my lines. And I can see the point of intersection. That intersection is 10, 130. Now it says explain what this means in the context of the problem. Well, if you label your ordered pair with the word sessions and dollars, that would mean that if you go and use the tennis court for 10 sessions, it does not matter whether you are a season holder or not, you would pay $130 both ways. Now, if you would go for less than that, it would be a better option to use the green line. In other words, don't have a season pass. If you use it more than 10 sessions, it would be better to use the red line, which would be to hold a season pass.